In the second video, I want to address more specifically this question of where is my activation? How is it that I know, how do I take the coordinates that I get out of SPM or FSL or whatever tool I'm using and use those to generate the more meaningful thing that I'm interested in is like, where in the brain is that? So roughly speaking, there are two ways to do this. One is to use sort of automated tools to help you, and then the other is to do it manually yourself. Ultimately, I suggest that if you can do it manually, that is going to be the best for you. But in practice, most of us don't have the neuroanatomy knowledge to do that. And even for those of us who want to, it may take years to develop sufficient information internally to do that. So all of these kind of automated tools provide help in getting to the point where you might be able to do this without reference to any of these other tools. So, personal example again, when I was a postdoc in Matthew Rushworth's lab in Oxford, and Matthew and Dick Passingham were two of my mentors, both of whom are, as I say before, amazing anatomists. So I would make an effort to understand what was in my data, but then one of the things I would do is sit down with either Matthew or Dick or both of them and go through the results. And just listening to the way they did it was amazing, because they had this internal knowledge of neuroanatomy that, I tried to approximate using these kind of tools, but going through it with a skilled neuroanatomist really dramatically improved both my motivation to learn it for myself, but also my ability to do so. It was invaluable. Now, the reality is most of us don't have access to a Dick Passingham or a Matthew Rushworth on a regular basis. And in those cases, these existing tools can be extremely helpful. So the first thing to talk about is what we talked about way back a few weeks ago in terms of atlases, right? And the original atlas that you could use would be the Talairach and Tourneau atlas. The coordinate system that we're using for all of our image analyses is the Talairach and Tourneau system. It's not, however, based on the Talairach and Tourneau atlas. If you recall, it's based on the Montreal 152 brain these days, and there are differences between them. But if you have access to a TNT atlas and want to have a look, it's relatively easy to do so because you get a coordinate for your activation. So, you get X is, is 56, Y is -4, and Z is 10. And then you turn to the relevant coronal section in the Talairach atlas, and you can see here in the top right-hand corner, this is a Y of -4, and I know it's Y because it's coronal and front to back is the Y plane. And I say, okay, well, I had a coordinate of X equals 56 and Z equals something which I've already forgotten. But I can say, okay, well, 56 is 5.6 centimeters. And I can just look on the x-axis to 56 and then go up to whatever it is the z coordinate is that I said it was and say, oh, look, that puts me in, the superior temporal gyrus, for instance. Now, bear in mind that Talairach and Tourneau were French, so, GTS is the superior temporal gyrus because in French it would be, my pronunciation's awful, but gyri temporalis superior or something like that, right? So, independent of the fact that my French is dreadful, the important point is that you could look up what GTS is, in this case superior temporal gyrus, and say, okay, so that coordinate corresponds to superior temporal gyrus. Now, you've got to do that with a bit of a grain of salt, because as I said, that coordinate might not be superior temporal gyrus in the Montreal 152 brain. It's going to be close, but it's only going to get you into roughly the right area. You'd want to check to make sure you were in that spot, and there are multiple different ways to check. So it's not a terrible way of doing things. It's not the one that I would actually recommend. But, if you have a TNT atlas, it's not bad. What I would say is because the Talairach and Tourneau atlas also includes Brodmann areas, so for instance, you can see that superior temporal gyrus is labeled 22. You might be tempted to say, not only am I in this particular anatomical region, but that corresponds to Brodmann's area 22. Don't go there. Okay, that's not correct for all the reasons that we talked about several weeks ago. It may or may not be the case that it's area 22, but Talairach and Tourneau did not have the cytoarchitectonic information in order to make those claims accurately on this atlas. So what I would strongly encourage you to do is ignore the Brodmann's areas if you're using the Talairach and Tourneau atlas. And as I said, this is why. This is literally the image that they had to convert into their atlas. So if you like, you could look at this image and make as reasonable a guess as Talairach and Tourneau did. In fairness, they were neurosurgeons, so their neuroanatomy was probably better than yours. No offense. But nonetheless, this is all the information that they had to work with. So that's why we're not taking these Brodmann areas seriously when we're taking them from the Talairach atlas. There are other ways to get Brodmann's information, and we'll talk about them. So this is kind of repeating things that we've talked about before. The Brodmann's areas were transferred by eye onto the atlas, so they're not very meaningful. The whole brain is based on the left hemisphere of a single person, which means that it's not very representative. As I mentioned previous lecture this week, even a very, very high resolution good brain like the canonical Colin 27 brain isn't necessarily accurate about what someone else's brain looks like. It's a really good picture of Colin's brain, but Colin wasn't in your study. The right hemisphere is a mirror of the left in the Talairach atlas, and that's just not accurate. There are differences between the right and left hemisphere, particularly anatomical differences that are lost as a result of that. And finally, none of the software packages are using the Talairach atlas. So it's not the optimal choice. If it's all you've got, it's a good place to start. You can do better, however. So any atlas based on the Montreal Neurological Institute brain is going to be better, for instance. Now, the things that make it better are the fact that it's not based on a single person or even a single hemisphere. It's a sample of the population. And it's what all of these softwares are actually using. So it's much more representative of whatever you've actually done. So what I'm saying here is, if you're going to look for a place, in terms of understanding the localizations, something based on 152 people drawn from the population is going to be much more representative, much more valid than something based on a single hemisphere of one person. Given that none of those people were involved in your study, it's still not possibly as good as looking at the structure of your participants, but that's a whole different level of difficulty because in doing that, you have to bring your own knowledge of neuroanatomy to bear. There isn't a template or an atlas based on your participants. Unless you're very, very lucky, that would be unusual. And as I talked about before, there are differences between the Talairach and the MNI atlases, and they're particularly evident as you move further and further away from the anterior-posterior anterior-commissure intersection of the midline. Sorry, that 000 point. So, for instance, when you get to the frontal pole, the occipital pole, the temporal, ventral parts of the temporal lobe, etc., that's where you start to see the most profound differences. Did I go backwards? Sorry, pushed the wrong button. And this is a visualization that Van Essen and Durker did that shows just how different they are. And you can see, as you move away from the midline, get to the more extreme areas, then you get greater and greater differences between them. And honestly, if you are, 8, 10, 12 millimeters off, you could easily be in a totally different anatomical region. That's not close. So there are atlases based on the Montreal Neurological Institute, and one of the more famous ones is what's called the AAL, which stands for Automated Anatomical Labeling. What happened was, oh man, another French name, and I'm going to butcher it. I'm sorry. Zurio Mazaye and her colleagues went through and took the Colin brain, which had been normalized to the Montreal Neurological template. So this is the canonical brain, and manually delineated both cortical and subcortical territories on that brain, and then labeled them, which is a heroic amount of effort, and it's a really, really good way to start looking at your anatomy. Because although it isn't going to be perfect relative to your data, it's at least much more representative of, of the general population, because it's one brain that's been normalized to a population template. So the nice thing about it is you put your coordinates in and you can see the crosshair there, and you can see that in this particular case it's sitting in the anterior part of the insula, and just knowing that you put the coordinate in, it pops out an anatomical label. So you don't have to know the anatomy, you can get some of that information. The warning here is exactly what I talked about previously in terms of putting this colon brain or the canonical brain as your background. Sometimes putting the coordinate in will give you a different result in colon, in the canonical brain, than it would in your participants. And I gave you an example of something like that in the inferior versus superior parietal lobules. So it's not guaranteed to be correct. It's guaranteed to be in the right area. But you do, again, still need to look further. This is a great place to start, but is not perhaps the right place to stop. There's something similar that Jeremy Schwalman did on the cerebellar atlas. So what he did was he took the colon brain cerebellum and then manually delineated all of the important regions of the cerebellum. So if you're interested in cerebellum as opposed to, cortex or even some subcortical areas, then there's an atlas of that based on the colon brain as well. The caveat with both of these is that although they're normalized to standard space, and therefore the same space that you did all of your data analysis in, they are based on single individuals, namely Colin, and he wasn't in your study. So you can get a level of precision that's misleading because it's not always accurate. The alternative are what are called probabilistic atlases based on the MNI templates. So there are various ones. I've illustrated two here. One's the Harvard-Oxford Atlas. One's the Lonnie Brain Atlas out of UCLA. And what's great about these is these are anatomy based on a sample of the population who's been transformed into the standard MNI space. As a result, if you put your crosshair on a particular voxel, you get a probability distribution that might say, for instance, oh yeah, this is 45% likely to be in pars opercularis, which is part of Broca's area. Maybe 30% likely to be in the inferior frontal sulcus, and then whatever's left, which I guess is about 25%, maybe it's ventral dorsolateral prefrontal cortex across your population. And that's really valuable. I mean, at some level it's frustrating because you don't have a definite single answer. But that's because there is no definite single answer, right? It varies across people. And the fact that there is this variance in terms of the interpretation accurately reflects the fact that that variance exists in the underlying population. If you want something more definite than that, then look in each of your individual subjects, overlay their activation on their brain, identify exactly where that location is in that individual, and then report that. But again, it's still going to be probabilistic unless it's the case that all n of your participants show activation in the same anatomical region. And when that happens, that's awesome. But no guarantees. One of the things I like about the Lonnie Brain Atlas is, in addition to giving you these probabilistic things, what it does is it tells you how they define those regions. So for instance, you can see in this particular image, there's an area shaded in sort of purple, and that's the inferior frontal gyrus. And then what you can do is click on that and it'll give you information. It's like, okay, well, that's bounded posteriorly by the precentral sulcus, superiorly by the inferior frontal sulcus. And then there are parts of the Sylvian fissure and the different rami of the Sylvian fissure that allow you to identify what the ventral and anterior borders are. In many cases, although that's sort of painful, you might not want that level of detail, that is precisely the information that's going to start to allow you to do this manual recognition of the anatomy. Because if you know what the borders are and then start to get good at recognizing those borders, say in your individuals or in a group, then you're no longer reliant on these kind of automated tools. You have the basic knowledge that's necessary for you to say with some degree of accuracy, this activation's in this particular anatomical region. In my experience, what happens is that you do studies over your career, and the regions that you're focusing on vary depending on the questions that you're asking. And as a result, personally, I've kind of built up piecemeal neuroanatomy in the sense that I focus on a region, I learn quite a bit about the anatomy of that as a result of doing that one study. Then maybe in a subsequent study, I'm working on an adjacent region or a totally different region, and I learn more about that. And then over the course of my career, I've built up a better understanding of neocortical anatomy piece by piece, study by study, rather than by trying to acquire all that information to begin with I mean, in graduate school, I took neuroanatomy classes, and they were incredibly helpful, but they provided a framework. It was the details, and the details that I got out of working with Dick Passium and Matthew Rushworth, and then doing this manual work with like the Lonnie Atlas, that allowed me to understand what a region was and wasn't, how I can see where it begins and ends, and can apply that to understanding and interpreting the locations of my studies. For what it's worth, Jørgen Didriksen has an excellent probabilistic atlas based on the M&I template of the cerebellum as well. So if you're interested in the cerebellum, I would highly encourage you to use the Didriksen atlas. And again, it's going to give you a percentage at each coordinate that it's in this region or that region, but that accurately reflects the variability that underlies the data that you collected. There are other tools and other things that you can use. So for instance, there's a software package called FreeSurfer that's pretty cool. FreeSurfer does this automated labeling of your participants' structural. So this is kind of brilliant, but it's time consuming and not the easiest thing to set up. So for instance, what FreeSurfer will do is if you feed in your structural scan, or the participants, single subjects participant scan, it will identify the central sulcus and the Sylvian fissure, and then from there we'll proceed to identify the major sulci around it and use those to parcellate that subject's brain into different regions. And you can see a parcellation here of a single right hemisphere. That's superb, right? Because this is a great way to start to learn some of the anatomy. And the other thing is it's unbiased, right? It's using the same criteria across every brain, every hemisphere. So there's no temptation for you to sort of hedge and be like, you know, I was hoping the activation was in the parahippocampus rather than the fusiform. And maybe, because there's this extra sulcus here, that is parahippocampus, you know, which happens. And it's inevitable. It happens to all of us. One of the nice things about using this algorithm that Desikan and colleagues developed in FreeSurfer is that you can avoid that kind of bias. The downside is it doesn't do a perfect job of identifying the borders. So where there are obvious borders, like the Sylvian fissure or the superior temporal sulcus, it's great. But there are other areas where it's a little bit trickier. I mean, for instance, identifying the difference in the inferior parietal lobe between the supramarginal border and the angular gyrus border. There are certain markers that you can use, but they're not present in every individual, and as a result, it makes some arbitrary decisions. The nice thing about those arbitrary decisions is they're unbiased. Then they would be consistent across participants. So if you have the time and the computational power to download and install FreeSurfer and use it to look at the anatomy of each of your individuals, then that is a very, very powerful tool, and it will help you to learn some of the anatomical areas. Unlike Lonnie, it doesn't tell you exactly how it did it, but it's still a great tool. Many people are really interested in relating their anatomy or their activations to not only the sort of macroanatomy, but the microanatomy through cytoarchitectonics. And this is possibly a result of the Talairach and Tourneau legacy, the fact that you could get it automatically out of that atlas, even if it wasn't right, it was there. But there's a group in Germany that was originally led by Carl Zillis and is now Carl and Katrin Ammons and some of the others who have come out of that lab, who are systematically trying to do probabilistic cytoarchitectonic mapping of the human brain in standard space. Now, this is an absolute labor of love, because to do this, they take postmortem brains and they scan them with MRI to get very detailed, accurate pictures of the anatomy. Then they subject them to histological studies, which are labor intensive, to say the least, to identify a region. So maybe in a particular case, they're interested in visual cortex, and they're interested in the difference between V1, V2, and V3. Brodmann's area is 17, 18, and 19. So they do this incredibly labor-intensive histochemical analysis of those regions, and then computationally reconstruct that histology back onto the MRI, and then combine those in standard space across those people to produce probabilistic cytoarchitectonic maps. It's kind of awesome what they're doing, but it's also an enormous amount of work. So as a result, they haven't done it for the entire brain yet. As years go on, that we're getting closer and closer, but it might mean that an area that you're particularly interested in may or may not be one that they've gotten to. The SPM Anatomy Toolbox is basically from the Zilis Ammons group, and I think it's Eichhoff who's the first author on these. But that represents the latest, greatest probabilistic cytoarchitectonic maps. So if you're interested in relating your results to Brodmann's areas, the way I would say you should do it is use the SPM Anatomy Toolbox. Or if you're not using SPM for whatever reason, then you should go to the raw maps that are provided by that lab. And you can overlay them on your anatomy and then see probabilistically, I'm in Brodmann's area 44, or I'm in 45, or I'm in 47, whatever the case may be. So all of those are tools to help you, as far as I'm concerned. First, localize your anatomy, or localize your activations, but second of all, learn the underlying neuroanatomy so that in the next time you run a study that's related to this area, you're more likely to be able to do it yourself, manually. Now, nonetheless, that's hard. And even if you're reasonably confident that you understand this area, you're probably going to make reference to some reference books, atlases, and there are a couple that I would recommend. But the importance here is that what you're doing is you're learning to recognize these regions based on their macroanatomic landmarks. That is to say, the gyri and the sulcal patterns, typically. It'll give you a much better understanding of the anatomy, but it'll also help you to develop sort of an internal 3D model of how the anatomy is related to one another. So looking at these 2D pictures is great, but sometimes it hides the complexity of the fact of the shapes, which are not always simple. Hippocampus is a beautiful example. I mean, everybody sort of knows that it's called the hippocampus because it's shaped like a seahorse. But then they look at one particular slide and they think, oh, it's a cross-section, it's by the amygdala, that's it. Well, the anterior head of the hippocampus is by the amygdala, but it's got this C-shaped structure that goes all the way around the Sylvian fissure, and it doesn't really tell you where the fornix is and things like that. So it's important to get this kind of 3D understanding of the anatomy, and that's just something that you develop over time. There's no point in rushing it, but there's no point in not doing it either. You might as well work on it, use those tools to help develop those skills. For me, the atlas that I find most useful is this atlas by Duvernoy. Yet another French name that I'm going to not pronounce fairly well. But what's great about this atlas is that it's got postmortem brains and it's labeled in detail. They're in multiple sections, so you can look at it sagittally, coronally, axial. But every other page or something like that, there's a corresponding MR image, a structural image, either a T1 weighted or in some cases T2 or in some cases proton density weighted. But nonetheless, there's an anatomical image from an MRI machine that you can reference to it. So it's very, very helpful if what you can do is say, I've understood some of the sulcal anatomy here, and I can see some of the key landmarks in my participant. I can find them on their structure, but maybe this is an area I haven't looked at before, so now it's up to me to sort of find the corresponding anatomy in an atlas, and I find that the Duvernoy atlas is invaluable for this. So this is an example of the fact that it's also got MRI scans in it. In this particular case, we've got a T1 weighted scan on the left and a T2 weighted scan on the right. But either way, it gives you the extra information that you need. All right, in terms of this week's take-home messages, there are a couple things that I'd like to suggest. First is, before you worry at all about what's significant and what isn't significant in your data, it's worth looking at your data using those faux color maps. Even if it's just to see what the basic patterns of results are across your groups, but also to see where there are data and where there aren't. And that allows you to track down why there isn't data. Is it distortion? Is it signal dropout? Is it because you have one or more subjects who, for whatever reason, don't have data in those areas and therefore they didn't continue on to the group? Whatever the case may be, that's a great place to start. I would then say use statistically lenient thresholds to look at what's significant, what's active in those maps. I tend to use a p less than 0.001 uncorrected, which corresponds to a z-score of about 3.1. But you pick whatever is sensible for you before you go to, okay, now I want to look at it with a corrected family-wise alpha level of 0.05. When you're doing that, certainly when you're looking at the regions that are significant, I would highly recommend that you absolutely plot the effect sizes across conditions in those regions, because the distribution of the way they show up will give you quite a bit of information. So for instance, if you haven't used any sort of inclusive masking and you've just done, say, a main effect, you may find that that main effect is not at all the main effect that you were expecting because of the things we talked about 2 weeks ago, I think at this point, which is to say that, you know, maybe it's all due to relative deactivations and you were expecting it to be activations. Those kind of things are really important. As soon as you plot the effect sizes, you can see whether it meets your expectation. And if it doesn't, that may be exactly the clue or motivation that you need to go back and add inclusive masks to ensure that you're getting the results that you think that you're getting. Even if you like Brodmann's areas, I would recommend avoiding the Talairach and Tourneau atlas in terms of localizing your activations. I would really highly encourage you to use any of the M&I approaches, and if you can, I would use the probabilistic approaches rather than the ones based on single subjects. I know you lose precision. You want a single answer for this voxel is in this part of the brain, but that voxel isn't always in that part of the brain, and that's the reality. That's the underlying truth. So probabilistic atlases that give you that uncertainty and say, well, it could be here, here, or here, are telling you what's really going on. And even though that means greater complexity for us as scientists trying to understand it, it represents the truth. So I encourage dealing with the messiness of probabilistic atlases. If you don't like that and you want to start with a single subject atlas to get a feel for where things are and then say, okay, now I understand the basics, what's the probability that that's the case? That's fine. That's a great way to do things. And then finally, whatever tools you're using, I would really highly encourage you to progress as much as you can through the complexity of these tools and learn the underlying neuroanatomy. Even if you're only learning the anatomy of one region in one particular study, that will still serve you in excellent stead throughout your career. So if you're going to be working in neuroanatomy and functional imaging, then the time that you invest in learning this material and developing your own internal 3D models of neuroanatomy, I personally think will be invaluable. You know, one of the papers that we talked about earlier in this term was a paper that Russ Poldrack and I wrote called In Praise of Tedious Anatomy. And this was one of the main messages that Russ and I were trying to deliver through this paper, was that it's painful. We get that. And it's been painful for all of us. But it's the kind of thing that pays benefits in the long run. So if you can take the time and do it, it's worth the efforts and you'll get some real returns out of it. The reading list this week is chapter 10 in the Poldrack, Mumford, and Nichols handbook. And as again, I have a whole slew of papers here. These tend to be less technical. That's not fair. They tend to be less mathematical than some of the papers in recent weeks, and therefore potentially more accessible. So for instance, Matthew Brett has a really fabulous paper from 2002 where he talked about the problem of functional localization in the brain. It's excellent, and I'd highly recommend it. It's, you know, nearly 20 years old, and the way they've stated the problem is still very appropriate. Simon Eickhoff has papers about the anatomical toolbox and how they actually, the Carl Zillis, Katrin Ammett lab, etc., are doing these probabilistic localizations of Brodmann's areas. And if that's something that's of interest to you, that paper is a must read. Carl Friston has a great paper called 10 Ironic Rules for Non-Statistical Reviewers. Honestly, I think that everybody should read that. It's very accessible and straightforward, but it deals with some of these issues. And then, look, there are others. There's a classic paper by Gary Loftus that isn't about neuroimaging. It's actually just about the importance of plotting your data and what you can learn from plotting your data above and beyond any statistical inference that you do. And they were talking about this in terms of reaction times and accuracy, so behavioral data. But this is essentially the main point that I've tried to make about plotting your effect sizes. It's exactly that same paper. Rather than go through all of them, I would just say that I think that the papers that are presented here are really iconic and essential reading. So I would encourage you to read as many as you can. Thanks very much for your attention. I'll see you next week.